Today, we want to go over some homework problems. Last time we talked about arc length and all right, we didn't really talk about linear and angular speed. I just said, hey, there are two different kinds of speed that are around here. Off you go. So we want to look at some of those problems today. Just really quickly before we begin, remember that arc length is just a more complicated version of circumference, or a more variable version of circumference. Arc length is theta times r, where theta is an angle in radians, and we multiply that by the radius. If we go all the way around the circle, then arc length is just the circumference, and our angle is 2 pi, and that's why our circumference is 2 pi times the radius. So we just took circumference and used smaller angles. We have two different kinds of speed. We have a linear speed and an angular speed. An angular speed is how many radians are going by, and a linear speed is how many distance units are going by. So distance units will be things like centimeters, inches, feet, miles. The time can be measured in seconds, minutes, hours, all kinds of stuff. But your angular speed will always be radians per unit of time. Radians per second, radians per minute, radians per hour, whatever time you're using. Another way we might list angular speed is to talk about revolutions per minute. We might talk about revolutions per minute. That's how many times we do a full circle. How many 2 pi do we get in per unit of time? We haven't started a problem yet. We're going to start with 6. It's on the list. Cool. So 33 RPM. I'm going to keep things slow so the numbers are lower. 33 RPM, so a record player speed, is 33 revolutions per minute. It makes one full circle 33 times per minute. One revolution will be a bunch of radians. It's going to be 2 pi radians. So one revolution is 2 pi radians. Because a revolution is going to be a full circle. So depending on if we want radians per unit of time, like we might want in an arc length calculation where their angle needs to be in radians, then we're going to want to convert our revolutions to radians. Let's take a look at some problems. Our first request was problem 6 from 3.3. Now, we all might have different values for the problem, so let's just take what we have here. Find the distance s a point travels along a circle over time 9 seconds. So time, 9 seconds. Given the angular speed, 4 pi radians per second. So this weird looking W is a lowercase omega. And the radius of the circle is 3 millimeters. Four pi radians per second. I just realized I'm on teacher mode, so we could see that the answer is going to be 339. So don't look at the answer. Don't look at the man behind the screen. That'll save me from having to go back and look. Oops, I keep clicking the wrong button. There we go. Oh, roll up. So we want to find out how far this point will go in 9 seconds. And we have an angular speed of 4 pi radians per second. So that's easy to calculate. That's 2 revolutions per second. So 4 pi is 2 revolutions. So we're doing 2 revolutions per second. This is a lowercase omega. So if your watch has one of these omegas on it, it would keep knock off. 4 pi radians per second is 2 revolutions per second. We don't need that right now, but interesting just nonetheless. Our radius is 3 millimeters, and we're going to see what happens in 9 seconds. So if we want to find how far, I can't remember what it was, this particle went, we need to know how many radians it went through. Because if we can figure out how many radians it went through, then we can multiply that by the radius, and that will give us the arc length. So we need to know number of radians. So S is equal to theta times R. Theta is going to be the number of radians we go through in 9 seconds. And R is going to be just the radius, which is 3 millimeters. So I have 9 seconds, and we're doing 4 pi radians every second. So how many radians are we going to go through? What's our theta in this case? If it was 1 second, how many radians are we going to do? 4 pi. So in 9 seconds, I just take the 9 seconds and multiply by 4 pi radians per second. So my theta is going to be 4 pi radians per second. And I'll multiply that by 9 seconds. So here we can cancel out the seconds, and we'll get 36 pi radians. We're just using that distance is equal to rate times time. In this case, our distance is being measured in radians. Our rate is radians per second, and our time is 9 seconds. So I multiply those two. Multiply your radians per second by second. So this is how far we went in radians, 36 pi radians. So 18 revolutions. Yeah. Theta is S over R, but I don't know what S is, right? S is what we're trying to figure out. So we're not at the arc length yet. We're just trying to figure out what the angle is. And the angle is going to be the angular speed multiplied by the amount of time. Now I can take this theta and plug it into S. The angle that we went through is 36 pi radians. And the distance, our radius is 3 millimeters. So I get 36 pi times 3, or 9018. So yeah, 36 times 3 will give us the 108. And then the problem says round this to the nearest unit. So that means we want an approximation. So 108 pi is unacceptable. So we'll do 108 pi and just get an approximation of 339.2. So 339. So what we needed in this case was two things. We needed, there was a question about the angular, there's quite a part of the problem about angular speed, and then a part of the problem about arc length. Arc length relates the radius of a circle and how far around the circle we go. So that involves the arc length, the angle, and the radius. So when we start talking about time and omega, the angular speed, what we needed here was that angular speed is angle divided by time. Or we could say that theta is omega times time. Or we could say time is theta divided by angular speed. So we needed a couple of things. We needed to convert our angular speed and time into an angle. Then we can take our angle and radius and put it into an arc length. Any questions? $339 or 108 pi. Correct. So if omega is theta over t, we have the 4 pi here. Theta is what we don't know, and t is 9 seconds. So then theta is 4 pi times 9. So problem 7 is the same problem with more steps. So problem 7, it's still find the distance s, find s. A point travels along a circle over time 9 minutes. Given the angular speed of 4 rotations per second. And the radius of the circle is 16 inches. And then we can make a note of this as a 3.43. Because I'm in teacher mode over here, so just ignore that. We'll come up with that. Your numbers are different anyway, so you're going to have to translate. So this problem, we were given the same stuff, but the stuff doesn't match up. That's the complication in problem 7. The next problem always has some more complications. So what's one of the things that doesn't match up here in our given information? I still have a t, I still have an omega, I still have an r. What doesn't match up here? What's the difference? Minutes and seconds. That's the first thing we should notice. Mismatch. So that's one of the complications. What's another difference between this problem and the previous problem? inches instead of millimeters, but that's okay. Inches only there, the inches only appears as inches. What's another difference between this problem and the previous problem? It is in inches, so it's going to be on. What's that? Yeah, we have rotations instead of radians. So 4 pi rotation, 4 rotations is how many radians? So I take the 4, how much is 1 rotation? How many radians is 1 rotation? That's in degrees, in radians, we want radians. 2 pi. So we'll take the 4 and we'll multiply by 2 pi radians. And so we'll have 8 pi radians per second. So that's another variation on this problem. Another change in the information that we were given. It's called 4 rotations per second instead of a number of radians per second. So we got to convert our rotations into radians. 4 rotations per second is 8 pi radians per second. So the other thing that we have is this 9 minutes, and our rotations per second is in seconds. The 16 inches, we can just deal with the 16 inches later. So how many seconds are in 9 minutes? Because I want to do, this is what we want to do. We know that omega is theta divided by t. Or if we want theta, that's omega times t. But omega and t have to be on the same clock. We can't be having t in minutes and omega in rotations per second. So if I want to keep omega at 8 pi radians per second, I got to figure out how many seconds there are in 9 minutes. So I want to use omega as 8 pi. I can't just multiply this by 9 minutes. Because minutes and seconds don't cancel out. How many seconds are there in a minute? 60. So I'm going to have to take this whole thing and multiply by 60. So that my minutes will cancel out. Or we can think about it in pieces. We just take the 9 minutes and multiply by 60 seconds, and that's 540 seconds. And we'll multiply the 540 seconds by 8 pi radians per second. And then our seconds will cancel out. So I need 540 times 8. So 4,320 pi radians. This is just the angle. Make sure we keep writing our units. This is going to be the angle that we go through. So we're going through 4,320 pi radians. And now we just have to put this at a radius of 16 inches. So S is theta times R. Now, this is a terrible measurement. You don't want to measure something in 69,120 times pi inches. That's ridiculous. I mean, we can measure this distance in inches, but it seems a little bit excessive. Like if there's a football game going on and they say, it's 4th and inches. Ooh, how many inches? You're thinking it's like close. But they're like, well, let's see, 10 yards, 30 feet, 360. It's 4th and 360 inches. Well, no, that's not good, but it's 4th and inches. So we probably want to convert this to something more useful. So first of all, let's get rid of the pi because it's weird to talk about this with the pi. So we'll multiply by pi. So this is 217,146.88 inches. Well, let's turn that into feet. Divide that by 12. That's going to be 18,095.57 feet. That's a little bit ridiculous. Let's cut that in. Let's turn that into miles. Yards might be better, but that's like dividing by 3. It's like 6,000 yards. That doesn't make any sense. I'll go divide by 300 and turn it into football fields. Or better yet, let's turn it into miles. So we'll divide by 5,280 to get 3.43 miles. So that'll give us some better units. Questions? In this problem, we go to miles because I think the problem tells you to do miles. Did it say to do miles? All right. In that case, that's why we go to miles. But in general, we have to figure out what would be the best. And the answer to how to figure that out is you'll just know. It will just make more sense. And it's just kind of hard to explain why one makes more sense than the other. You know what I mean? There are certain times that you just like know which one would be better. It's weird the things that we know and we can't explain. And where the explanation has clearly been retroactively applied. So I'll give you an example. This one's specifically like a native English speaker example, but I have a cute little green car. I would describe my car with these 3 adjectives. It is a cute car, it is a little car, and it is a green car. So it sounds natural to describe it as a cute little green car, right? And if I called it a green cute little car, that sounds weird, doesn't it? Or a little cute green car, that sounds weird. This is the one that makes sense. Why? Because the human brain is weird. So there's something about this number that just doesn't sit right with us. So we're like, oh, let's divide that out into feet. That's not very good. 18,000 feet, that doesn't make any sense. Unless I'm describing like the elevation of a mountain. Then we're like, oh, not use feet. Because how high is Mount Everest? 26,000 feet, which is more than 3.4 miles. Why don't we just use miles? It's like, oh, no. Mountains we measured in feet. But there's 26,000 of them. That's how we measure mountains. How far is your commute home? 4 miles. But that's like 20 some odd thousand feet. No. When you're driving, it's miles. But it's the same distance. Yeah, one of them goes up and it's a mountain. The other one is side to side and you're driving. So duh. I guess not. It's because we're picking really big mountains, right?
This mountain is 5 miles tall. Small numbers.
But no one's impressed, right?
20,000. Whoa. 20,000.
You're right. I'm going to go outside and I'm going to compete in the 300-foot dash. No. Yards. I don't know how anybody ever learned English. Can it be in miles? No. But you're moving, but you're not driving. You're running. Okay, so the marathon is a bunch of feet. No. That one is in miles. Why is that? Because you should be driving if it's 26 miles. That makes sense, right? I'm gonna go run a marathon. It's 26 miles. You should be driving that. No, I'm gonna run it. Like at Olympic sports, it's like the 1500 instead of the mile. But anyway, I would measure everything in football fields. No, washing machines is for jumping, obviously. If you're running a race, I'm going to do the 1 football field dash. All right, let's take a break, come back, and we'll do a couple more problems.